So welcome. I'm going to go over how to calculate the four main points of a titration. In particular, titration of a weak acid with a strong base. So here's a question. Let's see. So this is a titration. Okay, I'll try for my writing to get a bit neater than that, but still figuring this out. Okay, so here's a question. So we're going to calculate the pH at following volumes of base. So they're going to be the four typical ones we've seen in class. Before titration, sometime during titration, not equivalence, at equivalence, and then beyond equivalence. All right, so here we're going to figure out the pH of those different points. Let's see, volumes of base given. Here are values here, and we have 25. I just go ahead and I made the conversion within the question itself. So we have 25 milliliters or 0.025 liters of HClO acid. See, at a 0.2 molarity. This is being titrated with titrant 0.1 moles per liter of NaOH. Okay, so we'll do point A, or first question, or first part of the question. We'll say before titration. Okay, so at this point, it should be a straightforward Ka problem. Let's see if we can change colors here. See if it helps with the yellow. Okay, so this being what should be a straightforward Ka problem, here we have acid. Okay, we're going to go ahead and make an ice table. Okay, now if I forget to put AQ, don't mind that. There should be AQ. I should put states, especially since we're doing equilibrium and ice tables. You should always do it really, but if I forget, I'll try not to. But just so you know that there should be states. Okay, so this is the ionization of a weak acid, hypochlorous acid to be specific, in water, creating hydronium and conjugate base. Okay, now ice, as we've seen before from the question itself, we have a 0.2 molar concentration. That's right there. Now, because water is liquid, we can cancel that from our ice table. At time 0, we don't have any of these values. So as we've done in the past, this is going to decrease by amount x that is proportional to the balanced coefficient here. In this case, it's all a 1-to-1 ratio, so that makes it pretty simple. It's just minus x. If there were a 2 here, well, then that would just be minus 2x. But there isn't, so we just write minus x. And these concentrations of hydronium and conjugate base are going to increase by some value, again, proportional to the balance coefficient in the equation. Because it's 1 and 1, we just write plus x. Now we combine I and C, we get 0.2 minus x. 0 plus x is x, 0 plus x is also x. Now our Ka expression is going to look like this products, concentration of products over reactants. There is hydronium. Hypochlorous ion over reactants. We again exclude water. And there we go. Now we can plug in our known values. Now I'm going to end up erasing a good portion of this just to make some room here, but I can fill in some more. We get x from our ice table, rho E, and 0.2 minus x. Now, what I forgot to give you, probably wondering what's happening here, is a Ka value. You should always have a Ka value. Ka in this case is 3.0 times 10 to the negative 8. Okay, so I'll just add that to the question, change my colors again, and we're ready to go. Okay, so might as well plug that in here as well. 3.0 times 10 to the negative 8. Okay, now before I'm going to put a little arrow here, and it's going to look a bit, hopefully not too messy, but before we do that, I'm just going to write that the hundreds rule applies in this case. Now, don't need to show that it applies, but it does. Now, briefly to review that, if you were to multiply this by 100, so the Ka value by 100, it would still be less than the initial concentration of acid. If that is the case, then the hundreds rule applies, which allows you to do this. So let's continue just over here. We get there, that x here is excluded. Now you can go ahead and do this, and it'll take another minute or two, perhaps a bit longer, using the factor label method. I'm sorry, not the factor label method, the quadratic equation. Expanding, putting it into standard form, plug it into a quadratic. That'll work, and it'll give you an answer so similar to what we're going to see here that it's that is why the hundreds rule applies, and we will get a value of x that looks like this. Now, pardon the non-scientific notation here, but once we cross multiply 3.0 times 10 to the minus 8 by 0.2, and then square root both sides, we get a value. I will try to put it in scientific notation because it is a small number. So 7.7459 times 10 to the negative 5. Okay, good. So this is our x value here. Okay, now what this means is that we now know this value. Because we know that value, we can then plug that into our pH equation, right? So let's see. I'm going to erase. Not going to erase all the ink. What I'll just do is I'll erase the ice. Actually, oh look, I can scroll down. Let's just do that. Okay, so we'll leave it like that for now. Okay, so this is our x value. Therefore, because we've figured out what x is, we now know what the concentration of hydronium is that. So 7.7459 times 10 to the minus 5. Okay. Now we can plug that into our pH. So pH is equal to the negative log of the concentration of hydronium. So negative log of, we know what the concentration of hydronium is, 459 times 10 to the minus 5. I like to keep 4 or 5 digits ideally, or if you're doing this on your calculator, you can use the answer or the memory button to keep the entire entire value. Okay, so negative log of the concentration of hydronium is going to give you pH of 4.11. Now, from what we've seen in other examples in class, this is a little, relatively speaking, this answer is a little bit higher than we're used to. We're used to seeing around 1 point something, 2 point something, not even 3F. But what this tells us is we're going to hopefully see the same titration curve at the end, but it's just going to start a little bit higher, right? So it's still acidic. We have a 4.11 pH. Okay, now I'm going to erase everything now, but remembering, I'll bring it up again as it becomes relevant. If I can get to, I think I'll just do this. Okay, so 4.11 is our first point, and therefore part A is solved. Okay, and erase everything, but part A is now solved. We'll review again what the question is. It's going to scroll up. Okay, so back just to go over what we're now solving for. Okay, so B. B says we're going to solve for pH at 5 milliliters of NaOH. Okay, so before we go ahead and do that, I like to call this a background calculation. We're going to determine how many moles of acid, of HClO, we have. At the very beginning, before anything happens, this is a background calculation. So let's figure out number of moles. Moles are equal to C times V. We know the concentration from the question. It's 0.2 moles per liter. We know that we have 25 mils, or 0.025 liters. Don't forget that conversion, so liters and liters cancel out. And what we're left with is 0.005 moles. Okay, the other thing, so this is the background calculation, but more now specific to what's happening in part B or in question B, for 5 mils of NaOH. Okay, so this on the side here, at 5 mils of NaOH, this is going to happen. I'll switch colors here because we're actually solving for something now. Okay, so N, again, equal to C times V. Okay, we have a 0.1 molar concentration, moles per liter, of base, again, from the question itself. We have 5 mils is 0.005 liters. Again, liters and liters cancels out. And we're left with 0.00, there's an extra 0.5 moles of NaOH. Okay, we are set and ready to continue. Now, student once aptly named this ice table not an ice table. I used to call it a fake ice table, but we're going to do what I'd like to call now, thanks to this student, a nice table. Now, it's called a nice table because it's not quite an ice table. Ice tables use concentrations. Here we're going to use moles instead. So what's happening at this point of the titration is you have, you're beginning to neutralize the acid with the base that's being dropped into it. Now, that means you're going to have water present, you're going to have base completely consumed, you can have less acid present. So essentially we're going to have this. So HClO, almost forgot the states. Okay, then we have some sodium hydroxide. Now that's dropped in. We know exactly how many moles. We'll figure that out later. Or we'll put that in just a bit. All right, H2O. Yep, we know that neutralization produces water and a salt. In this case, it's going to be, oops, not that, sorry, erase this. Okay, so this is the beginning of our nice table. Remember, not really a nice table, but we can say initially there is a change, and then what happens at equilibrium, but not quite. We'll talk about that in just a bit. So we have these many moles, right, of acid from our calculations above. We have that many moles from our calculations above of base. Now, for a couple of reasons, I'm going to exclude that. There is no salt, of course, and we move on. So here we have, originally we have that much acid. Now, because we've dropped this much base into it, we know that we're going to end up, just to save some room here, we're going to end up, I'm going to put it there, subtracting that amount of base, because it's being neutralized quantitatively. So it's being pushing the reaction forward direction. This base is consuming this acid through this neutralization reaction. And because we consumed base and acid, the base will also consume itself but in this very neutralization reaction, which will give us, at, if you want to call it equilibrium, not quite equilibrium, but at this point it is no moles of base, right? We normally don't include water, so I'm just going to say done, done. Here, what we can say, but see, because this is not really concentration, it's moles. Despite me putting this line right here, I am going to write, just so that we're clear, hopefully, that you do have this many moles of water. Now, this is being a nice table where N is for moles. We do have some water created. Now, normally in these ice tables, we don't include, we exclude water, but for our reasons, because it's a nice table, we're going to include it. Okay, we have this much, or these many moles, right, of salt. We have, let's just rewrite water. I plus C, we get 0 plus that, and that gives us that. So we have these many moles. Okay, just realized it didn't line up at all. Okay, but essentially, this value minus that value gives us 0.0045. Okay, no base, and we have that value here of water and that value here of salt. Okay, the other thing that's happened, so now we have our number of moles of acid has changed. We have acid present, but the other thing that's happened importantly is volume has changed. So originally we had 25 milliliters of acid. I'll just write HA for short for acid. Then we also added 5 mils of base, right? So that means if we add this up, we get 30 mils, right? Or 0.03 liters in total new volume. So total volume is 0.03 liters. Now this is going to change. It's going to change concentration because it's after all a new volume. So let's see if I can scroll down again. For some reason clicking here seems to work. Well, I'm going to have to start erasing. Okay, so it looks like I'm going to have to start erasing. So let's see. I'll continue from where we left off, but again, remember, new volume, we have this many moles of acid, 0.0045, and that many moles of salt. Okay, erase this. Okay. Now, what's really being calculated here is still the equilibrium calculation of the dissociation or ionization of this acid. So in water, I'm not going to create a new ice table here because this is just to remind you that we know that we have a certain amount of acid present, and I forgot to write states. So let's fill that in here. Okay, and then conjugate base. Good. Our Ka value or Ka expression looks like this. Right, reactant over product, concentrations of, okay, before we write anything else, we know moles, right? Remember our nice table? Write this down. We know from our nice table, we were able to figure out moles. We also have a new total volume, right? That means you're going to, so therefore, this means you're going to have new concentrations as well. So therefore, new concentrations. Anything that is relevant here. Remember, we're solving for hydronium, so we need to figure out what the new concentration is for conjugate base and acid. Let's do that to the side here. Okay. New color, just to make things nice. Let's try this. Let's try this blue. Okay. So um, let's start with acid. Okay. So the concentration of HClO is going to be moles over volume. We know it's 0. From our nice table, 0.0045 moles, and volume is 0.03 liters. That gives us a new concentration of 0.15 moles per liter. Okay, so this is done. Okay, so check there. Now we have to do this one. Okay, so okay, now this is where I have to make a little bit of a side note here. Yes, it's still moles over volume, but what we figured out from our ice table, from our nice table, is that that the number of moles of actually figured out this. So we figured out the number of moles of NaClO. So that is not this. These two are not the same, but this will dissociate in a 1-to-1 ratio. So if you know the number of moles of NaClO, we therefore know the number of moles of just this ion, right? So without showing you the 1-to-1 dissociation equation, then we can assume then that the number of moles, because of this 1-to-1 association, is going to be the same. So from our previously written out nice table, we have these many moles, right? Moles divided by a new volume is that, and we get this concentration. I like to keep digits. Moles per liter. Okay, good. Now we have solved, oops, accidentally drew that, but that's a strange check mark there. That still works. Okay, so back to yellow. Okay, now we can start to fill in. We know what Ka is given to us in the question, 3.0 times 10 to the minus 8. Okay, we know, well, we don't know actually what Hc, oops, don't know what happened there. Okay, we know this value, right? Concentration of ClO. We just figured it out to the right in blue there. Still getting used to this pen. We know this concentration as well. Okay. Now, without boring you with some grade 9 math, I'm going to go ahead and just give you the value for hydronium. Okay, what you do, cross multiply, solve for that. There you go. So it's 3.3 times, you know what, I missed a few digits there. Okay, 3.332 times 10 to the minus 9. Okay, that means we know the concentration then of hydronium. We can now again use our pH equation, log concentration of hydronium, negative log, plug this value in, 3.332. Okay. So second point now, pH is, again, it's going to seem a bit higher than what you're used to, but we expected that. There you go, 8.48. Second point is done. Okay, let's see if I can, I think I'll just erase. So you can pause if you'd like to see this again, but we're going to erase all this for now. Second point, let's change colors because we're going to do next part, C. So for C, at equivalence. Now we don't know volume of base. No, that's okay. It just means, however, that we need one extra small step. We know, though, that at equivalence, even from grade 11, we know that number of moles of hydrogen or hydronium is equal to the number of moles of OH. Now, since, here's the logic behind it, hopefully you can follow, since in our case, our acid, remember that background calculation we did? Since our acid, this perhaps should be in yellow, but it's okay. Since our acid has that, we had that many moles exactly of acid from the beginning, we therefore need the same number of moles of OH, the same amount. No, so we have to figure out now what volume gives us this amount. So volume is equal to N over C. We know these values. We know that we're going to need that many moles of base. We know the concentration of base given to us in the question, right? Moles per liter. We can then figure out that we need 0.05 liters or 50 mils of base to reach equivalence. So let's go ahead and change this color. Okay. Now at equivalence, let's write this down. At equivalence, the only thing that's present, so the only ion that is the only important significant ion present is, well, we would also have sodium, but we know that that's a neutral ion, is at equivalence we have this ion present. So is present. Okay, therefore, it will behave like this with water. And I'm almost forgetting states here. That's supposed to be an L. Okay. So this is behaving like a base. It follows the Bronson-Lowry definition of bases. It will gain a hydrogen ion. There you go. It behaves like a base. So this has now become a Kb problem, or you can write a Kb expression for this. So products, concentration of products over reactants excluding water because water is a liquid. And here we now have a Kb expression. Now we're going to end up solving for OH, the concentration of OH, but we can't do that because we don't know what Kb is yet. We do have Ka. We know the water constant Kw is equal to Ka times Kb. So a little bit of grade 9 algebra here. We have Kb is equal to Kw divided by Ka. Kw is 1 times 10 to the negative 14. That's a 14. Divided by Ka given to us in the question is this. So Kb is then also quite small, 3.3 times 10 to the negative 7. Right. So that's one important thing that we've accomplished here. The second thing we have to do is our volume has also changed. New volume again. Right, so if you remember, we have originally we have 25 mils of analyte of acid, and we're going to add 50 mils because we figured out here that we need 50 mils to reach equivalence for a total of 75 milliliters. Now we're going to convert that, into liters. Now the concentration then, new volume means our third thing, new concentration. So concentration of ClO is moles of this ion, which we know to be this. Now how do we know that? Well, okay, so back to our background calculation here. Neutralization will push the reaction quantitatively forward completely. Even though you might be thinking, well, it's a weak acid, doesn't completely dissociate. It will because of this neutralization reaction. And because our acid in this case was HClO, and it dissociates in a 1-to-1 ratio, we have that many moles, 0.005 moles of conjugate base, this guy. Okay, so we have that many moles. We're going to divide by our new volume. So our new volume, 0.075 liters. And we have a new concentration, 0.066 moles. I believe it's 66 continuing, and I don't know why I didn't keep more digits, but there it is. Okay, now if I can get to that scrolling part, let's see how did I do that? Aha, okay, so good. So the third thing, we now have our new concentration. So back to Ka. Sorry, KB. Okay, I'm going to make an ice table now, a real ice table. So, and although I've already written it up there, go ahead, let's just do this again. I probably won't include states because I feel like I already have. Although you definitely should. I'm going to now. That's an L. And I'm getting used to this pen, so bear with me. Here. Okay, so I, C, E. Okay, 0, our new concentration, 0.066 being a real ice table. We exclude water completely. Let's not talk about that again. We don't need to. Times 0, 0, 0. Now it's all minus x, as we've seen before, plus x, right? All proportional to their coefficients. In this case, they're all 1. I plus c, it gives us this expression at equilibrium. 0 plus x is x, 0 plus x is x. Okay, now, where should we do kb? Let's do kb here. Okay, so our kb expression is equal to x over 0.066 minus x. We're going to write hundreds rule applies. Now we know what kb is. We should have put it in here. Okay, so kb, 3.3 times 10 to the minus 7. Ooh, I'm kind of squeezing this in here. 3.3 times 10 to the minus 7. Okay, we can get rid of x because the hundreds rule applies. Multiply this by 100, it's still less than the initial constant, or the initial value here, right? So, or if you don't want to do that, you can spend an extra few minutes and do the quadratic equation. I'm going to jump ahead a little bit of grade 9 math here. Cross multiply, square root both sides, and we get x is equal to 1.47 times 10 to the negative 4. So think about what we've solved here. We solved for this value, right? We now know what concentration is of OH, which is important because using that information we can figure out what pH is, just a few small steps. Okay, so just to make this extra clear, I'm going to write this down. This is the concentration of hydroxide. Okay, now this allows us to do, I'm using these steps, you might as well. So our third step was to figure out the new concentration of conjugate base. Our fourth step here is to create an ice table, plug into our Kb expression, find out what x is. Our fifth, it looks like a 9, it's a 4. Our fifth step is then to figure out what POH is. Now there's a couple ways to do this. This is just one, but it makes the most sense to me. Well, they all make sense. It's just what your preference is. So I'm going to, oh, this is, I'm getting ahead of myself. I'm missing a 1 there, right? It's just this value here. So minus 4. Oh my, that looks like a 9. Okay, all right, so POH, okay, once you've plugged that in, will be 3.83. We know we want pH though, right? Not POH. We know that 14 is the sum of pH plus POH, right? That means pH is equal to 14 minus POH. I'm going to write it to right here, not down, not that much room. So 14 minus 3.83, and we get 10.17. That is our pH at our third point, which is at equilibrium. Again, a little higher than we're used to seeing, but we started off a bit high. We're going to continue this trend. Okay, third point, done. No more room to scroll down, so I'm going to have to erase the page, and I'll remind you what the question is asking us to solve for. Okay, so 3 points done. On to the last point. See if I can scroll up. Okay. So D. D said 2 milliliters past equivalence. Now, remember what this means. Some pre-calculations here. 2 milliliters past, right, means we have this happening. New volumes. Might as well do new volume. We have the original 25 from the acid, right? Then we have the 50 needed to reach 50 milliliters of base needed to reach equivalence. Then we also have 2 mils added on top of that, right? So that's 25, 50, 2. That gives us a new volume of 77 milliliters, or 0.077 liters. Okay, switching colors. Okay, so what this means. New volume. Let's also figure out how much at this point. Let's figure out with 2 mils of NaOH at a 0.1 molar concentration. We're going to figure out the number of moles. Moles equal to C times V. We have 2 mils added, right? Liters cancels out, and we're left with 0.0002 moles. Now we do have at this point, we have conjugate base present, very little of it. We know the Kb value for that. The only significant source of ions here, the only significant source. Let's write this in red because it's important. The only significant source. So only and most significant ion present is or comes from the 2 milliliters of base. That means you can ignore everything else. Okay, so that means concentration, because we have moles now and we have a new volume. We can figure out concentration is 0.0002 moles. Divide that by a new volume, 0.077 liters. That gives us a concentration of, and I'm going to keep a bunch of digits here. We want to be as precise as we can. Right? That's a new concentration, 0.002597 moles per liter. Now, this tells us a concentration of NaOH, knowing that it is a 1-to-1 ratio, right? we know that the concentration of OH is exactly that number. So knowing this, we're going to plug it into our POH like we did in the last point. POH is pH equation, negative log of the concentration of OH, 0.002597. Okay, and we get 2.585. This means pH finally is 14 minus POH. Right, explain that in the last problem or in the last step. So 14 then minus 2.585 gives us a final pH past equivalence of 11.41, and this is our answer. That's it. So again, this is going to look like, just to review, if I can scroll down a bit, not too much space here, but just to review, if we draw a titration curve, so let's see how straight I can get these lines. Okay, draw a titration curve. We're going to get, right, so pH values here. Let's just say for point of reference that this is pH 7. Don't like how that looks. Okay, so pH is the y-axis, volume of base, right, is on the x. Okay, so initially we had, let's say, value 4 points. Let me look back at what I have here. 4.11, I believe. Yeah, 4.1. All right. So initially, zero base added, we have a approximately, okay, this is not the scale, obviously, 4.11. Then we added 5 mils of base, and it went up to 8 point, maybe I'll write this down here, 4.11. Then when it went up to 8.48, quite high. Let's modify this scale. I'm not liking how this scale will look like. Ooh, that erased everything. Okay, that'll do. Okay, start it off about here. Okay, 4.11. Then this goes up. I'll have to continue this up here. And this goes up to 8.48. So let's say about here. Okay, 8.48. Now notice, now this is very exaggerated. There's an increased or significant change in pH here. This should eventually plateau, right? Our next point, the pH of our next point, if I recall, it's here at 10.17, right? And this is at equivalence. So let's say it's somewhere, probably somewhere, sure, somewhere up there. So it should gradually go up and suddenly like this. So when that happens, okay, that will be at a pH of 10.17. Okay, that will plateau again. After 2 more mils were added, we got a final pH of 11.41. So let's say that's about here, 11.41. Now, this isn't ever that pronounced, right? But I'm drawing this for the first time. Using this this pen, this is what we've called a buffer region here. We'll talk more about that in class. Equivalence point is above 7. Now we haven't seen this much above, but we did start off higher, so it should make sense. After adding 2 more mils, we get a second or last point here of 11.41 as our pH. And that is a titration of a weak acid with a strong base.